Okay, so welcome back to the Oxford Discrete Maths and Probability Seminar. So our second talk today, it's a pleasure to have István Tomon, who's going to talk on graph discrepancy.
Okay, so thank you very much, and thank you very much for the invitation. So as this is a probability and combinatorics joint seminar, I wanted to bring something that's kind of related to both, and I think discrepancy theory satisfies this criteria. But what is discrepancy theory actually is about? So the general question we are interested in is that given some kind of system, where this can be a graph, sequence of integer, point set in the space, or whatever you want, and how smoothly can it be distributed? And we ask this in the sense that, so can we find an instance of the system where kind of every subsystem of the system is very close to its expected size in a certain sense? Maybe to give you an example, so one of the classical problems in discrepancy theory is about how well can a subset of points be distributed in the unit square. So here, let's say we have, sorry for not the best picture. So here, let's say we have the unit square. We have a bunch of points inside, and then we measure the discrepancy of this point set with respect to axis parallel rectangles. So we look at kind of all the axis parallel rectangles. We look at how many points fall inside, and we compare it with kind of how many points we expect it to fall inside, which is just the number of points times the area of this rectangle. And so now we are only looking at axis parallel rectangles. We look through kind of all kind of selections, and then the discrepancy is this kind of maximum error we can find. Yes. And then the problem we are interested in is that what is the point set which has kind of the nicest distribution, which is where this discrepancy is minimized. And let us denote this function by f. And then the question is like, okay, how small can be the discrepancy of n points? So one kind of natural candidate you can think of is if you put the points in kind of a grid-like structure. In this case, the discrepancy is not hard to see that it's roughly of the order square root n if you place the points in a square root n by square root n grid. Because it is at least square root, because you can, sorry, it's hard to draw with the mouse, but you can kind of put a rectangle containing a complete column, which is very narrow, so its area is tending to 0, while the number of points is essentially square root n. So we will see that the discrepancy of this is square root n. But then another natural candidate for a point set with small discrepancies, you just take the points randomly. But in this case, you can again see that the discrepancy is around square root n. So in general, when we want to we think about certain systems with smooth distributions, always a natural candidate is to take a random system in certain sense. But we know that for random, the deviation is always around square root n, so we have this kind of error term always. But now the question is, okay, we have seen this kind of two natural point sets with small discrepancy. Can this be beaten? And yeah, it turns out that there are some much more well-behaved sets, so-called van der Korput sets, or in higher dimensions, so-called Horton sets, which only have logarithmic discrepancy, and it can be shown that kind of this bound is the best possible. So you always have discrepancy at least logarithmic. And now, while this problem in the plane is well understood, it's already a major problem that what happens in higher dimensions. So in dimension D, there is a polylogarithmic gap between the lower and upper bound. So it's still known that the answer is fully logarithmic, but now there is some gap there. And some people call this as the great open problem of discrepancy theory. But yeah, but what I want to talk about is not geometric. I want to talk about a problem in discrepancy theory involving graphs. So how do we define the discrepancy in the case of graphs? So suppose that we are given a graph on n vertices which edge density p, and then we will measure the discrepancy of this graph with respect to the induced subgraphs. So we are looking at the following quantity. We are scanning through all subsets of the vertices. We look at how many edges are induced by this, and we subtract the expected. So the second term is the expected number of edges if this subset of vertices was chosen randomly. And we are again asking what is the maximum absolute value of this deviation. Another question we are interested in is that if we are given this parameter p and then the number of vertices, then what can be the minimum of the discrepancy, and also what kind of graphs minimize this discrepancy. So in other words, how smoothly can be the edges of a graph be distributed. Again, we can look at what happens for random graphs. So it's easy to see using standard concentration arguments like Chernoff that if you look at the average training random graph G and P, then this has discrepancy around square root P and to the 3/2. And here I'm only looking at P at most 1/2. And the reason is that it is to see that the discrepancy of a graph is the same as the discrepancy of its complement. So I can assume that I have its most 1/2, but if P is greater than 1/2, I just need to replace this P with 1 minus P. Okay, now the question is again, is random the best, or can we beat random? Are there graphs with even smoother distribution? And here, as it was shown by Erdős, Goldbach, Park, and Spencer in the 80s, the answer is no. So indeed, the random graph has the smoothest distribution. Every graph has discrepancy at least square root P and to the 3/2. Okay. But again, let's go back a bit to the definition of discrepancy. So again, we are measuring the deviation from the average, and this deviation can be either a positive deviation or either a negative deviation. So we either have this many more edges, or we have this many less edges compared to the expected size in an induced subgraph. So therefore, it's kind of a natural question to ask that what happens if we only want one of them? So let's say we only want a large positive deviation, or what if we only want a large negative deviation? What can we say in this case? So therefore, we can define the following quantities. We can define the so-called positive discrepancy. So this is the same expression as before, just without the absolute values. So now we are really looking at how much more edges do we have compared to the average. And similarly, we can look at the negative discrepancy, where we look at how much less edges do we have compared to average. So what is the kind of deficit of the edges do we have? And note that both the positive and negative discrepancy are non-negative numbers. So the negative discrepancy is also a positive quantity. And similarly as before, now the question is that given these parameters P and N, what is the minimum of the positive discrepancy, and similarly, what is the minimum of the negative discrepancy? But in most of my talk, I will concentrate on the first question. So I will look at the positive discrepancy. So again, you can note that if you take the complement, then the positive discrepancy becomes a negative discrepancy. So these quantities are still closely related. But okay, so what can we say about these quantities? So if you see this problem at the first time, it is kind of very easy to get this intuition that these this shouldn't differ too much from just the usual notion of discrepancy. Of course, we know that if we average this quantity, this EGU minus PU, which is to over all subsets of U, then the average should be 0. So then somehow you would expect that if you have large positive discrepancy, then this should even out with large negative discrepancy. And then this kind of suggests that these two quantities shouldn't be that different from just the normal discrepancy to begin with. And indeed, if we look at the case of the random graph, there is no difference. So again, with standard concentration arguments, the positive discrepancy and the negative discrepancy are both of the order square root p times roughly n to the 3/2. However, if I show you this next example, you can easily see that this intuition was completely false. Because if you just look at the complete bipartite graph, so you have vertex class of size m and all the edges between, then this only has positive discrepancy linear in n. But on the other hand, this has negative discrepancy quadratic in n. So this shows that the positive discrepancy can be much smaller than just the discrepancy alone. So this constant n is much smaller than this n to the 3/2, which you would expect in the p equals 1/2 case. On the other hand, this intuition that this positive and negative discrepancy should be roughly of the same order, this is also completely false, because here we have a very small positive discrepancy and we have a very large negative discrepancy. And now it actually somewhat surprisingly turns out that this kind of phenomenon is true in general. So if one of them is small, then the other one should be very large, which was proved in 2006 by Alon-Boppana and Scott. So they proved that in general, if p is at most half, then the product of the positive and negative discrepancy is always at least some constant p to the cubed. So on one hand, this immediately shows that at least one of them is always the square root of this, which is exactly the bound you get for random and the bound you get for just the normal discrepancy. On the other hand, this inequality also shows that both the positive and the negative discrepancy are always at least linear in n. So this is true because neither the positive nor the negative can be larger than Pn squared. So then both of them need to be at least linear as well. And as we have seen before, this linear can be achieved. So the complete bipartite graph is n, and in general, all the Turan graphs have linear discrepancies. So here the Turan graphs are just the complete R-partite graphs where all the parts have the same size. So again, here just using our notation, we just showed that f1/2 is linear in n, so the minimum of the positive discrepancy at p equals half is n. However, we can see that Turan graphs are very special. So are there some other examples of graphs which have very small positive discrepancy? And if you start to play around a bit with graphs, you can quickly find that it's very hard to construct graphs with positive discrepancy. So with its model positive discrepancy. So other than Turan graphs, there are really no kind of obvious examples which even improve on this square root p n to the 3/2 bound. So motivated by this, Räty conjecture that the moment before we are a bit bounded away from 1/2, so as long as p is just an epsilon less than 1/2, then we should have the same bound for the positive discrepancy as we had for the normal discrepancy. So in this case, we should have at least square root p n to the 3/2. Now, before I talk about results, concerning this conjecture, let me just give you some other motivation why we are interested in this positive discrepancy at all. So it turns out that the positive and negative discrepancies are very closely related to some other well-studied parameters of graphs. So first of all, they are closely related to the max cut problem in graphs. So if you don't know, the max cut problem in a graph asks for what is the maximum number of edges in a cut. So here a cut is just a partition of the vertices into two parts, and we are asking what is the maximum number of edges we can have between two parts. And there is this kind of opposite or analog of this max cut problem, which is the minimum bisection problem, where we ask that what is the minimum size of a cut. But now we need this condition that we cut into two equal sized parts. Otherwise, we could just have zero edges if one of the parts is empty. So for this to make sense, we need to assume that we cut into two equal parts. And it turns out that we have the following relation between max cut, minimum bisection, and the discrepancies. So the max cut is essentially the number of edges over 2 plus a constant times the negative discrepancy. So here, this first term is kind of the trivial bound. So if we look at a random cut, so random cut in expectation cuts every edge with probability half. So the expected size of a cut is EG over 2. So when we are asking about max cut, we are usually asking about what is the surplus, or what is this additional number of edges we can get above this number of edges over 2. And this extra quantity, which is sometimes called the surplus, this is asymptotically equal to the negative discrepancy of G, in case G is regular. So here, this is an important condition, otherwise it's not true. And similarly, the minimum bisection is just the number of edges over 2 minus a constant times the positive discrepancy. And it turns out that this kind of analogous question, so this question I had about the positive discrepancy, this was already studied in the setting of minimum bisection in the 90s by Alon. So Alon proved that if we have a deregular graph where D is much smaller compared to n, then the minimum bisection is always at most dn over 4, which is just the number of edges over 2 minus this quantity we can call the deficit, which is of the order constant square root dn. Or equivalently, this theorem is equivalent to saying that if G is deregular, then the positive discrepancy of G is of the order square root d to the n, which is exactly this square root p n to the 3/2. So this is exactly the quantity that was conjectured by Verstraete. Okay, so this theorem of Alon shows a lot of evidence towards this conjecture of Verstraete. However, there are two kind of issues with these theorems. One is that we need to assume that the average degree is much smaller compared to n. So we really need that these at most n to the 1 over 9. So in particular, the argument of Alon needs that somehow you can find many edges which are at least distance 8. So his argument doesn't really extend to largerly. And the other kind of issue is that we assume regularity, and in this conjecture of Verstraete, there should just work for every any graph of average degree d. So now let me show you what we managed to prove. So we proved that what we proved is that the conjecture of Verstraete is actually false. So somehow the behavior of the minimum positive discrepancy is much more nuanced. It's much more mysterious than one would actually believe. And what we showed that this minimum positive discrepancy goes through several phase transitions. So we can show that the minimum positive discrepancy of n-vertex graphs of average degree d. So first of all, we have this same bound square root, the n, which continues to hold until d is of the order n to the 2/3. However, after this point, something happens, and the minimum discrepancies start to decrease, which is fairly surprising for us, and it has the order of n squared over d. So this continues to hold until n to the 3/4. However, unfortunately, after this point, we don't really have matching lower and upper bounds, but we still know that this lower bound n squared over d continues to hold even up to n to the 4/5. And unfortunately, we don't really have. So here the issue is more the upper bounds. However, at the point n to the 4/5, we can show that the positive discrepancy starts to increase again. So after decreasing, it starts to increase again. And this continues to hold up to really this point conjectured by Verstrata. So as long as we are a bit bounded away from n-half, so just as long as we are a bit bounded away from the complete bipartite graph, we still have a substantial discrepancy. And we know that this same bounded square root dn still cannot hold in this regime. So there are some constructions which show that the positive discrepancy is at most n to the 4/3. So maybe here is a picture showing our results. So here, so here is a change in monotonicity. Here is a change, or we kind of conjecture that there is actually a change here, and then suddenly when we are approaching 1/2, then this function drops very sharply. So these are kind of our results, and here there is some gap, but we have some reasons to believe that our kind of lower bounds, or not these lower bounds. So I will show you some later results which show that this function should somehow grow like this. It somehow should be between the upper and lower bound. That's okay. So now let me talk a bit about the proof of this, or where do these functions come from. So first of all, how to even construct graphs which have small positive discrepancy. So in the first regime, we don't have to do anything. So here, just random graphs show that this bound is optimal. So random graphs, no matter what regime you look at, they always give square root d. So in these other regimes, you somehow have to beat random. But then how can you control the positive discrepancy of a graph? So it turns out that the positive discrepancy is controlled by the second largest eigenvalue of the graph. So let me show you a simple lemma which says that if G is a deregular graph with eigenvalues λ1 up to λn, then the positive discrepancy is at most λ2n over 2 plus d. So the proof of this is mostly just a standard linear algebra argument. If you've seen the expander mixing lemma or anything similar, this just follows in the same lines. But still, let me show you because it's not long. So just consider the adjacency matrix of the graph and let v1, vn be an orthonormal basis. Then if U is a subgraph, sorry, is a subset of the vertices. Again, we are interested in this quantity, the number of edges in U minus the expected number of edges of U, which is P times U choose 2. So now writing X for the characteristic vector, we can just rewrite the left-hand side in the following form. So this will be equal to 1/2 times the X transponent times AX minus P, so the density times XT, minus the all-one matrix minus the diagonal, the identity matrix times X. And then writing this characteristic vector in our eigenbasis, we get this formula. And as you would expect, the first terms, the term containing lambda1 just cancels. And we can upper bound all the other terms using lambda2. So we get that this quantity here is at most 1/2 lambda2 times the sum of the coefficients squared. Plus we have this error term, which will not matter. So this error term is at most this. So we get that this is at most lambda2 to n over 2 plus d. So we get that indeed the positive discrepancy is controlled by lambda2. However, maybe it's good to point out that that the other direction is not true, so you cannot really prove a lower bound on the positive discrepancy with the help of lambda2. And the reason is that the positive discrepancy is kind of a global property, while lambda2 can be large because of some local issues as well. So for example, if you pick the union of a complete graph and a large sparse random graph, then lambda2 will be large, but the positive discrepancy will be small. So this is really just an upper bound. But now if we know this inequality and we want to come up with graphs with small positive discrepancy, then we just need to come up with graphs with small lambda2. So unfortunately, I actually have no idea how to construct such graphs, but luckily there is a really big literature of these algebraic constructions of graphs, in particular strong irregular graphs, where people documented the eigenvalues, and just going through this huge literature, we could find a number of interesting graphs, and it was kind of this fortunate situation that there were graphs which kind of matched our lower bounds. So we could find some graphs in the literature that that somehow really coincided with what we wanted. So we could find a strong irregular graph which have average degree, which is n to the 3/4 regular, and it has second eigenvalue n to the 1/4. So this gives a graph which has positive discrepancy only n to the 5/4, which gives exactly this behavior n squared over d. So this is kind of so this is the graph that kind of witnesses this point, and then we can just randomly sparsify this graph to get everything here in this regime. And also we could find a graph which is dense, so it has average degree n/3, but the second eigenvalue is only n to the 1/3. So this gives a graph with positive discrepancy n to the 4/3. And sorry, so this is the graph which witnesses this point. But now this business with the second eigenvalue might remind you of some well-known theorem called the Alon-Boppana bound. So let me just mention this. So this this is a well-known result about the second eigenvalue, which tells us that if a graph G has diameter at least 4, then the second eigenvalue is always at least the square root of the regularity of the graph. So more precisely, the statement says that if we look at a family of graphs with increasing diameter, then the lambda2 is always, then minimum of the lambda2 approach is 2 times square root b, and it is known that this bound is the best possible. But the Alon-Boppana bound, so it really needs this condition that the diameter at least 4. So now looking at these results with the positive discrepancy, it naturally, so this question naturally arises that what happens if for denser graphs, so maybe graphs that are still not too dense but still has diameter less than 4. And together with Igor Bala, we also looked at this problem, and it turns out that we get for the minimum of the second eigenvalue, we get a very similar behavior than we get for the positive discrepancy. So this Alon-Boppana bound, it turns out that it holds for as long as d is still at most n to the 2 over 3. So again, it's the same bound as for the positive discrepancy. We have this behavior n over d in this regime, and now we know it's between d to the 1 over 3 and n to the 1 over 3 is at least n to the 3 over 4, and is a bit less than n half. And again, we cannot go up to n half because at n half we have the complete bipartite graph, which just has second eigenvalue 0. But here this gives this very interesting kind of behavior that as long as just we are a bit less than n half, we know that the minimum of the lambda2 is of the order n to the 1 over 3, which is again kind of unexpected. That where does this exponent 1 over 3 comes from? So this is not something you would ever guess if you look at the Alon-Boppana bound. Okay, but so this is what I wanted to say about the upper bounds. So let me talk a bit about how to get the lower bounds for the positive discrepancy. So in particular, let me show this kind of simplified version that if G is the regular graph and D is less than n to the 2/3, so this is the first regime, then the positive discrepancy really behaves as for the random graphs, so that we always have at least square root d to the n. So how to prove this theorem? So now the idea comes from semi-definite programming, and in particular, it is inspired by the Gilmans-Williamson algorithm, which is a celebrated algorithm used to find the maximum cut in graphs. So the idea is that we will assign certain vectors to the vertices of our graph. So here, these will be the vectors, but now let's say just we want to assign some vectors, and now what we will do is we will pick a random half space and look at all the vectors that are contained in this half space, and this will define the set of vertices which will witness large positive discrepancy. So if we have this assignment of vectors, so for every vertex we define the vector xv, where xvw is 1 if v is equal to w, xvw is 1 over square root d if v and w are neighbors, otherwise we write 0. So note that as G is the regular, we have that the length of the vector is square root 2. So all the vectors have the same length, square root 2. And now And also these vectors are designed in the way so that if we have two vertices that are neighbors, then the events that they are both contained in the same random half space should be positively correlated. But we kind of also want that vectors that are not connected, they are somehow negatively correlated. But so how to calculate this correlation? So I claim that now with this choice of vectors, so I claim that actually in general, so no matter how we assign vectors to the vertices, the probability that both of them lie in the same half space is going to be roughly 1/4, which is the probability if they were independent, plus essentially the scalar product of xu and xv. Maybe let me try to draw it. So let's say I have these two vectors, xu, xv. Then it turns out that the probability that this random half space contains both of them only depends on their angle alpha. So if this alpha would be 90 degrees or pi/2, then this corresponds to the fact that these events are independent. And then if we are a bit away, so this probability just depends linearly on the angle, and when this angle is close to 90 degrees, then this can be very well approximated by the scalar product of the two vectors. So we get essentially this formula. Okay, but now if we have this, then so this is a vector. Again, we want to show that with this random selection of u, we get a large discrepancy. And so what we will show in particular then that the expected size of this discrepancy we get from this random set is already going to be of order square root dn. But now if we have this idea, then this is kind of an easy calculation. Because what we can observe is that so first of all, the expectation of the number of edges in U. So we just sum for all edges U the scalar product, plus we have this term 1/4, minus we have for all pairs U the scalar product xuv. But the reason I don't have this 1/4 is that the 1/4s in this sum cancel the 1/4s in this sum. So this constant term disappears, so I'm really just left with this, with essentially the sum of the scalar product minus the sum of the scalar product weighted with the density. So but now the main observation is that the way these vectors are designed is that when u and v are neighbors, so there will be at least one coordinate where, so when these are both neighbors, then the scalar product will be always at least constant over square root d. Because when this is 1, here the other vector will be 1 over square root d. So it can be larger, but it is always at least 1 over square root d. So this first sum is large. However, we also have to make sure that this second sum is not too large, so this is small. And now what we can do is the way we can calculate this sum, we just go coordinate by coordinate. So we are just summing for all uv. So now each common neighbor of u and v will add an extra 1/d factor. So this 1/, so when we look at the scalar product, we can only have terms of the form 1 over square root d, 1 over square root d. And we will have those only for the common neighbors of u and v. So we will get exactly this sum. But then note that this sum, or this double sum, actually just counts the number of cherries in the graph G divided by the number of cherries. So every vertex gives exactly this d squared cherries. So we have a total of n times d squared. But then this d squared, so then we are left with the d squared. So we get that this expression is roughly of the form square root dn minus d squared. But note that the left-hand side will be strictly greater than square root dn as long as these is much less than, so it's a constant times less than n to the 2/3, which was exactly what we wanted in our theorem. So this is kind of the proof in this case. Okay. But now what can we say about the others? So let me go back to this theorem. So this takes care of this part. Now it turns out that the second part is very similar. So in order to get this n squared over d bound, we just choose our vectors slightly differently. So again, sorry for jumping that back and forth, but here the only difference is that instead of putting 1 over square root d, we put some slightly less number here. We put some x where x is, think of the order d over n. Yeah, I think if I remember correctly, yeah, we just put here d over n, and the exact same argument works. However, when we get to this bound, this d to the 1 over 4n, so this is somehow completely different, and this is somehow completely linear algebraic. So while these kind of arguments may have a bit of combinatorial shadows, so I could imagine some way to turn it into a combinatorial argument. So the proof of this is somehow heavily relies on linear algebra, and we use a lot about the eigenvalue decomposition of the graph. So we use some deep linear algebra. We use some Hadamard products. So the proof of this is considerably harder than anything we do here somehow, and we have no idea how to even talk about this combinatorially. So which is very surprising for us. But still, we don't think that this d to the 1 over 4n is sharp. We believe that the actual truth should be this bound. So here you can see that we get a bit stronger results about the second eigenvalue. So instead of d to the 1 over 4, we actually know that it grows essentially as d to the 1 over 3. And we have some strong evidence to believe that this should give actually the right order for both the positive discrepancy and for both the second eigenvalue. However, it seems like that the real challenge is coming up with constructions. And again, as all these constructions come from the strong regular graphs, which from these very algebraic constructions, which seem to be some entirely different area of mathematics, which I'm not an expert in. We don't really have an idea how to get these constructions. Yes, but so this is sorry, where was the bound? Let me leave this here. So this is more or less all I wanted to talk about. So it was a bit faster than expected. Sorry for that, but thank you very much for your attention.
István, thank you very much. Would anyone like to ask questions? Actually, I have one question. Can you say anything about hypergraphs? Do you have anything at all?
We are looking at it right now. But so one thing that goes through, so these two arguments, they give something for sparse hypergraphs as well. But we we don't really know beyond what happens.
Other questions? Okay, in that case I will.
Is there more than one notion for hypergraphs? Because for a graph, you could look at the number of edges meeting a set or the number inside, and they're the same because the number of edges meeting a set is all the edges that are not inside its complement. And does that mean for hypergraphs, you could look at edges entirely contained within a set, or having, if it's 3 uniform, or the number having 2 vertices in a set, or 1 or 0, but the last 2 are the opposites of the first, but maybe only one of them actually interesting, not sure.
Yeah, so Bolabash and Delax, they look at this notion of positive and negative discrepancy also for hypergraphs, where they look at these edges really inside. But then there are also results of Colon, Kwan, Sudakov, where they look at cuts in hypergraph, which is basically when you are looking at edges which contain at least one vertex in both parts. And in this case, they show some interesting results. Yeah, and they consider some mixture of this. So yes, these are studied, but there are a lot of questions that's not very well understood.
Baylor and I also looked at intersections of pairs of hypergraphs. For instance, if you fix one hypergraph and then think about what happens with a second one, and that captures that there are some interesting phenomena that don't appear for graphs. Okay, maybe I'll pause the recording there and carry on chatting.